Welcome back. This is lecture 20. So up until now we have been discussing noise figure, or rather we have been discussing how to calculate noise figure for a given network. We took the example of a common source amplifier and we saw what are the handles that we have to reduce the noise figure, right? Prior to that we also discussed about how to design a circuit for matching, right? Because when you are designing a receiver, it is imperative to ensure that the input of the receiver is also matched to a 50 ohm load, right? And also if it's a amplifier, it also has to give gain, right? So then what are the three things definitely we need to ensure in a low noise amplifier that is sitting at the front end and it is connected to the antenna interface? So number one, it needs to give matching. It needs to be, the input should be matched to a 50 ohm load. Number two, it should have a good noise figure. What is a good noise figure? We haven't yet defined. Ideally it should be 0 dB, but we know that that's not possible. And number three, definitely it should give some amplification, right? So right now till now we have dealt with almost all three of them, but in silos. So the purpose of this lecture and the next lecture is also to combine these effects and then see what are the possible design topologies that we can come up with, right? Okay, so but before going there, let me tie up on a system level perspective what is the implication of noise figure and matching at a system level, right? What do I mean by that? So essentially we have an antenna which is receiving signal, and I am not including the filters which are generally upfront. But let's say we have an LNA, and let's say this is a 50 ohm matched. Okay, and let's assume that the LNA has a noise factor of f, right? Okay, and let's further assume the LNA has a gain of g, power gain of g. When I say power gain, I'm taking the output power divided by the input power. Just like voltage gain, you have output voltage by input voltage. Power gain is output power by input power. Okay. For this calculation, the gain is not required, but let's keep that aside for the time being. Okay. So now what I would like to understand is what is the implication of noise figure for a system designer, right? So what is the noise factor? Noise factor is one of the fundamental definitions of noise factor is it is SNR in by SNR out, right? Now what is SNR, which essentially means that SNR out is SNR in divided by F. Okay. Now what is SNR in? SNR in is nothing but what is the input power, that is P in, right? What is the input power divided by the input noise, right? Now what is input noise? How have we modeled this? We have modeled this as a voltage source and a series resistance RS, which is 50 ohm, correct? So what is N in then? N in is essentially the 50 ohm noise, right? Noise from the RS. Okay, so what is N in then? Or I should say, in this case, if I am interested in the power spectral density, I should say SVN in, right? So what is SVN in? SVN in is 4 kT times times Rs is the noise, that is the noise voltage that is getting generated through Rs, times a factor, right, times a factor which corresponds to the division ratio, right. So to make it absolutely clear, so if you have Rs here, and if your LNA interface, LNA antenna interface is matched, then this Rin is also equal to Rs under reflection match condition. Now this is Vn, this voltage is Vn over 2, right. So what is the noise voltage, what is the noise pass spectral density due to the input noise only? So this is noise pass spectral density due to Vin, right, divided by 4, right. So this is, or rather, if I have to be strictly talking about power here, right, not with respect to a unit impedance, then what should I say? This is nothing but the power here is Vn square by 4 Rs, right. So essentially I get the pass spectral density to be 4 kT Rs times 1 over 4 Rs, right, because the pass spectral density corresponding to Vn square is 4 kT Rs, and due to matched load I get 1 over 4 Rs. So I essentially get AT. But this is also not sufficient, because this is pass spectral density, which means this is per unit per hertz, right, per unit bandwidth. Now strictly speaking, this should not be pass spectral density, because SNR is supposed to be unitless, right. If Pin is in watts or milliwatts, the denominator should also be in watts or milliwatts, which means that this should also be multiplied by the effective bandwidth, right. So which means that your SNR in, which means my SNR in is En divided by KT times B, correct? Okay. So what is SNR out? So your SNR out essentially becomes SNR in by F, which is P in by KTB times F. This is in linear scale. If I go in dB scale, so if I go in dB scale, then I can say that SNR out in dB is P in dBm, right. So I can convert if P in and KTB both are in dBm, then I can use it in I can essentially use the same unit, right. So this is minus 10 log KT, and if I say divide by 1 milliwatt, so that it becomes dBm, right, minus 10 log B, right, minus 10 log F, which is noise figure, right. Okay. So by the way, this B is in hertz. Okay. Okay, fine. So what is this telling us? So before saying what is it telling us, let me rearrange this this expression a bit. So I'll keep P in one side. So I say P in dBm in one side, which is equal to this minus 10 log to the base 10 KT is essentially minus 170. So 10 log KT in dBm is happens to be at room temperature happens to be minus 174, right? dBm per hertz. So this becomes minus 174. This is dBm per hertz, right? Uh, then you get plus 10 log bandwidth in hertz, right? Then you get plus the noise figure. Okay, so this is at 290 Kelvin. Okay, so what is this expression telling us? This expression is telling us that under matched condition, right? Okay, I have missed that SNR out. That's the most important part, right? So this plus SNR out in dB. This expression is essentially telling us if I desire certain signal to noise ratio at the output, right? Let's say I require certain signal to noise ratio at the output to understand what the transmitter which is located far away is sending me, right? So if the SNR out is, let's say, 0 dB, which means that I have as much noise as signal, which means that probably I'll not be able to distinguish the noise from the signal or the signal from the noise effectively, right? If we want to distinguish the signal from the noise, it is expected that the signal should have higher power. Whatever I receive should have a higher signal content than noise content, right? So in mathematical terms, that essentially means that we should have SNR out which is more than 0 dB. So now, depending upon what backend protocol you have, you will be told that I need only this much SNR out. So as an RF designer, you will be told by the system level guys, system level designers, he or she will get you she will let you know that, hey, I want this much SNR out. I want 10 dB. At least I want 10 dB, or at least I want 20 dB, or at least I want 8 dB of signal to noise ratio at the output of your LNA or at the output of your system to at least make sense of something what we are going to receive, and nothing gets drowned under the noise. Okay, so given that SNR out is a specification, this will be a given spec, and the given and you know that 174 dBm per hertz, you cannot do anything. The bandwidth is also typically a given spec. It is driven by the protocol, right? So in this expression, what is not a given spec? When I say not a given spec, what I mean is it's not fixed by the protocol, right? Is noise figure. So what is this telling us? Is this telling us that if I want a signal to noise ratio of some value, fixed value, right? I need to have certain amount of P in at the input of my receiver, given that my receiver has certain noise figure. Other way of saying the same thing is, if I am targeting certain P in, right? If I am targeting certain P in, then from this formula, I can back calculate what is the noise figure of the receiver that I want. Now, if somebody tells me, right, so I mean, this formula is a quick and will give you a quick and dirty estimate of whether things are doable at all or not. So, for example, if somebody tells me that I want an SNR out of, say, we want SNR out of 20 dB, right? And let's say my bandwidth is 1 megahertz, right? So what does this expression boil down to? My P in, minimum P in, right? So this is the minimum P in that I will require is minus 174 plus 10 log of B, which is 10 power 6, because the B is in hertz. This effectively becomes plus 60, right? Is plus noise figure plus SNR out is 20. So your P in dB is essentially, this is my minus 174 plus 80, which is 94, right? This is in dB or dBm plus the noise figure. And so what is this telling us? This is telling us if you want an SNR out of 20 dB over a bandwidth of 1 megahertz, then your minimum sensitivity or minimum amount of power, signal power that should arrive at the antenna should be minus 94 dBm plus a noise figure. And the noise figure cannot, cannot go below 0 dBm. Noise figure cannot be negative. So essentially what it is telling us is that the minimum signal power that must appear at the antenna port is minus 94 dBm plus noise figure. And if somebody, now can you tell me, if somebody tells me that no, my base station is so far away that the minimum power that I can give you is minus 100 dBm, but I want to ensure that this specification is satisfied, what will your answer be? You can say that I cannot make anything with negative noise figure, right? So if P in dB is if you are guaranteeing that the input power is minus 100 dBm, right, which essentially means that you are asking me to make a noise figure of, get something with a noise figure of minus 6 dBm. Sorry, I'm not a magician, right? So I cannot do that. So that the value of the noise figure. That's why it's a very quick and dirty estimate to figure out whether the specification that you are targeting at the first place is doable or not, right? In most cases, it will be doable. The engineer or your friend who will be giving you the specification also knows this formula, right? So one will not give you a specification which is not doable, right? But now let's assume that it is doable. Then what is your noise figure telling us? So essentially your noise figure is, so let me define this, whatever this minimum signal power that must appear at the antenna port to ensure given or required SNR out is called the sensitivity of the RX. Okay, so now let's say you are designing a receiver which has 3 dB noise figure, right? Or rather, let me say, if you are designing a receiver which has 6 dB noise figure, so what is the sensitivity for this particular specification? So naturally, if I am designing a receiver for 6 dB noise figure, my specification, my minimum P in, the sensitivity will be minus 88 dBm. And versus, I tell my system engineer that no, I have a noise figure of 3 dB, right? Which means that the sensitivity suddenly improves to minus 91 dBm, right? So when I say improve, what I essentially mean is that now my handset or the antenna, my antenna port can work with even smaller amount of received power, which means that the tower that I am able, probably the base station to which I can communicate can be farther away than my current location. Or in other words, from a very broad business perspective, if your noise figure is lower, you can get away with smaller number of base stations, right? So you need lesser antennas because your handsets are more capable of operating with smaller signal power, right? So essentially, you see that naturally, yes, noise figure has a very top level, system level importance. It directly relates to finances in some way, right? So that is why RF engineers, especially who are working in receivers, are extremely finicky about noise figure. The first thing that it is assumed that your receiver input is matched, and it is assumed that the LN is giving some gain. The first thing, almost, if you are designing a receiver, is what is your, the first spec is what is your noise figure. Okay, so that is why your noise figure specification is extremely critical. Okay, so now that we have understood the importance of noise figure from the perspective of sensitivity of a receiver, let's go back to our good old common source amplifier, right? Because that's a stage that gives gain, right? So let's go back to that structure and see whether it can, is it good enough, or it can give, if we need to optimize it further, right? So again, so you have an antenna. Again, I model it like a voltage source with an R, and then we have a common source amplifier, and maybe we have an inductor, and we have done this analysis multiple times. We know that there is a CGS capacitor associated with this, and we know that this cannot match, right? So what should we do to match? The simplest way to match is to put another R, which is equal to RS, right? So as long as so for frequencies for omega much less than 1 over whatever is the equivalent capacity resistance seen across the CGS, which is RS by 2, right? So RS by 2 times CGS, right? We have, this is Z in, so we have matching, right? If you want to prove it rigorously, all you have to do is find out the reflection coefficient gamma at this interface, right? So what is gamma at that interface? So it's basically ZL minus Z naught by ZL plus Z naught. In this case, ZL is effectively is R parallel 1 over j omega CGS, that is R by 1 plus j omega CGS minus R, or RS by RS by 1 plus j omega CGS RS plus R, which effectively becomes 1 minus 1 plus j omega CGS RS divided by 1 plus j omega CGS RS, which is minus j omega CGS RS by 2 plus j omega CGS RS. If I take the 2 out, so your reflection coefficient effectively becomes minus 1 by 2 or minus j by 2 omega CGS RS by 1 plus j omega CGS RS over 2, right? So if you are operating at a frequency where omega is much lesser than RS CGS over 2, right? So which essentially means that omega times RS CGS over 2 is much less than 1. So essentially your gamma, right, becomes much lesser than 1, and mod of gamma becomes much lesser than half. So essentially you see that you are approaching the matching condition, right? Okay, fine. So now this much we understand that we need this extra R. Okay, so if we need this extra R, then what is the impact? Even though it matches, this extra R will give me an additional noise, right? So earlier, what was the noise? So earlier the additional noise that was coming from was only from this RS, Now additional noise is also coming from the matching resistor RS, right? So if for example, if I simply neglect, if I neglect the effect of CGS just for the sake of simplicity, right? So for omega much lesser than 1 over CGS RS by 2, which essentially means that I can neglect CGS. So your circuit essentially becomes this. And if I am interested in the short circuit current, then all I need is what is the noise contribution due to the source is V N in is the noise contribution due to RS, right? So V N in. So this essentially is here you get V N in by 2, and if I am interested in the short circuit current, so this is I N out. So in this case, your IN out will be Vn in over 2 times Gm, right? So essentially, your spot spectral density becomes 4 kT Rs over 4, right? Because we are squaring everything, right? Times Gm squared, right? So this is noise due to the input only, right? And what is the total noise at the output? So SV in out total is clearly this noise will obviously will be there. So let me simplify it. This is KT RS GM squared by 4. I should not say SV because we are taking output current. So SIN due to input, SIN total. So this will be this term. For KT RS GM squared, bit more accurate. So I'll get this term, then I'm going to get an identical term because of the additional R, right? So I get 2 KT RS GM squared, and I get an extra term because the transistor is essentially giving me noise, and the spectral density of that is 4 KT gamma GM. So what is your noise figure or noise factor? Noise factor is essentially this divided by this. So I get 2 plus 4 KT gamma GM by KT RS GM squared. So KT goes, 1 GM goes. So you get 2 plus gamma by GM RS times 4, right? Okay. So now you see that what is the minimum noise figure that you can get? Let's say you design your GMRS to be your RS you cannot change. Let's say you design your GM such that GMRS is much greater than 4 gamma. So naturally your noise figure min that is possible is 3 dB, right? So 10 log 2 is 3 dB. So that is the minimum noise figure that you can get. Now, what is the why do you have this minimum noise figure to be 3 dB and not 0 dB? It's because now you have this factor of 2 here, right? This 2 plus. And why are you having this 2 plus? This 2 plus is happening because you have one noise contribution that is coming from the source and another noise contribution that is coming from the additional R. So if I basically break this down, so this is KT RS GM squared plus KT RS GM squared, right? So this is coming from source RS and this one is coming from matching RS. So just because you have put something for matching that is contributing to identical amount of noise. Because it is contributing to identical amount of noise, you have a noise figure of 3 dB. Now compare that to something where you, let's say hypothetically, let's assume you have a scenario where you do not have matching, or rather you have matching without, your matching element does not really contribute to additional noise. So then you can naturally see that you can knock off 3 dB easily, which probably a matching resistor otherwise would have provided, right? So what is the crux of the matter? The crux of the matter is that there seems to be a trade-off between matching with a resistive element in a common source amplifier and the noise figure that we get. Now you might say, why common source amplifier? Why not a common gate amplifier? We understand the common gate amplifier also has is a way of matching. Sure, but I will not prove this to you, but I will submit this, that even if you have a common gate amplifier, RS, and let's say the input impedance, that is 1 over GM, is equal to RS, you design it in such a way that this is true. But even then, the matching is being done by this transistor, and this transistor is noisy, and that noise will come out, and it will again add up to an excess noise due to the matching network, right? So as long as you are using a noisy element to do matching, there is no, using a single transistor circuit, there is no way of getting away from that extra 3 dB noise figure. Okay. So now the solution is, I mean, if there is a solution possible, then obviously it cannot be done using inductor. It cannot be done using resistors or transistors because both are noisy. So we'll have to take help of the noiseless elements in the network, which are essentially capacitors and inductors, right? So before understanding how to go about thinking about matching using capacitors or inductors, let's understand what is the fundamental problem of using capacitors and inductors for matching. The fundamental problem is they are imaginary. Their impedances are imaginary. They have a phase lag with respect to the input. If you want perfect matching, you do not want that phase lag, right? So you want real impedances. So now the question boils down to, how do I use inductors and capacitors to get real impedances, right? So what I essentially am pointing out is, so what is the root cause of that imaginary part of a capacitor, impedance offered by capacitor or inductor? The root cause is there is a delay, there is a phase lag. If there is no delay between the voltage that you apply and the current that you get, or the current that you apply or the voltage that you accrue at a particular port, then you know that the port impedance is perfectly resistive. If there is a delay, then you know that the port impedance has an imaginary part, right? It will be either inductive or capacitive based on the amount of delay between voltage and current, and whichever leads or lags. Okay. So now the thing is, we want to use inductors or capacitors for matching, which means that I want to use an inductor or a capacitor, but I want to put it under in a certain condition so that there is no delay between the voltage and the current. So obviously having an inductor, only grounded inductor, will not solve the purpose. We have to wrap something around the inductor, right? So at least that much we understand, right? So what is the issue? So again, let's start with a capacitor. So let's say we have a capacitor. So the thing is, we need to put something around it, right? So let's say I have a capacitor. I need to put something around it such that when I push in a voltage or a current, let's say for the time being, I say that I put in a test voltage. This current I test must be in phase with V test, right? Or at least some part of this I test should be in phase with V test, and then I know probably this contraption has a real part, right? Okay. So now the question is, I mean, if this is an LTI element, it will have some transfer function h of j omega. So what is this transfer function? and what can we do about it, right? This somewhat looks like it looks like I'm leading towards Miller kind of scenario. Not necessarily, but it is similar, right? So let's assume that the voltage transfer function between the two ports of h of j omega at a particular frequency h of j omega naught is a e power minus j phi, right? So at a particular frequency, if I change the frequency, a might change, phi might change. I'm not talking about all frequencies, because ultimately, see, I mean, we understand that one good thing about our RF system is that they can be narrow band, right? They can be concentrated within certain band, and we don't care what is happening at the other bands as much. Okay, so if I can even get a real impedance using inductors and capacitors or imaginary elements across a very small band, I'm good, right? So that's the assumption, that's the hope. So if this is the case, then what is V naught? So V naught will be essentially V test times A times e to the power minus j phi, right? So then what will be I test? Okay, so which essentially means that your I test is the difference of voltage times j omega c. So your I test is essentially V test minus V0 times j omega c, which is V test 1 minus a e to the power minus j phi times j omega c. So in other words, V test over I test is 1 by j omega c 1 minus a e to the power minus j phi, which means your Zin, which is V test over I test, is nothing but, I'll keep 1 over j omega c as is because this is easy to handle. The other part I will multiply with the conjugate in the denominator and the numerator. So I get 1 minus a power j phi by basically mod of 1 minus a power minus j phi squared, and the numerator essentially is, if I split it up into real and imaginary, so I get 1 minus a cos phi minus a sin phi by j omega c some real, right? Which essentially means that your Zin has a real part which is equal to this, and this combined becomes minus a sin phi by omega c times mod of 1 minus a to the power minus j phi whole squared plus an imaginary part, right? Okay, so now the key thing to note is that we have a real part. This is the real part. So what can we essentially derive from this? The intuition that we can derive is that if you have a h of j omega, right, where there is a phase lag between the two ports, and you put a contraption, if you put a capacitance across the port, then you end up with a negative real impedance. But what if you have a phase lead between those two ports and you put a capacitance? Then obviously then phi becomes essentially negative. If you do the sin phi becomes negative, so essentially you end up with a positive real impedance. So what should we look for? Again, from the context of a common source amplifier, right? So from the context of the fact that we want a common source amplifier, we want this to be the main contraption where I do not want to tamper with the place I am applying the input. So this application point of the input remains constant, but I have to find another part of the amplifier where I get a phase lead with respect to the voltage, right? So now where can you think of I can get a phase lead? Now note that what is the genesis of phase in a common source amplifier? Moment you apply a voltage, let's say I increase the voltage, the current will increase, right? And if I just think of from the perspective of phase lead means what? But if if there is a phase lag, which means there will be a delay between application of the voltage at one port and the voltage, some voltage appearing at the other port, right? And if there's a phase lead, there will not be any delay at all, right? It will be instantaneous. Okay. So now if I consider these two terminals, gate and the source, if I consider this terminal between the gate and the source, having a phase lead means I'm pulling the gate up and the source immediately pulls up, right? Source cannot be grounded. Source immediately pulls up. So what kind of contraption do you think I should put to get a phase lead, right? Now, when I say immediately pulls up, if it just follows it, it's not sufficient. It has to go up at a faster rate. Because if I just put a resistor, it also goes up, but it doesn't go up at a faster rate. So in order to get a lead, I have to use something which goes up at a faster rate than a resistor. I mean, essentially, which means that I need some frequency dependent component, and capacitor doesn't do. What else can I put? Resistor is ruled out, capacitor is ruled out. So only other thing is inductor. So let's try with an inductor, right? So we'll put an inductor here. Correct? And we have to put again, like with respect to the example before, we'll have to put a capacitor between these two nodes. But fortunately, a capacitor already exists, and the capacitor is our CGS, right? That already exists. So what I'm looking for now, I'm looking for the impedance looking into this port, right? So instead of overcomplicating our scenario, so what I'll do is I will apply, just like before, a test voltage, and I am going to find out the effective impedance, and again I am going to do it assuming it's a short circuit, drain is short circuited, right? I mean, no harm done. So if this is a test voltage and this is I test, right? So what is the VGS? So your VGS in this case is essentially I test by j omega CGS, correct? So what is I out? Your I out is GM times VGS, which is GM times I test by j omega CGS, correct? So what is this voltage? Let me call this Vs, the source voltage. Your Vs is nothing but I test plus I out going into, let me call this L, j omega L, right? Which is, again, I know that Vs is nothing but V test minus I test by j omega CGS, which is I test plus I out, which is GM times I test by j omega CGS times j omega L. So if I put all the terms together, your V test becomes I test times 1 plus 1 by j omega CGS. Sorry, it's not 1 plus, right? J omega L plus. This is j omega L plus. This term goes, then I get another term, that is Gm times j omega L by j omega CGS, which essentially means your V test over I test becomes j omega L plus 1 by j omega CGS plus Gm times L by CGS, or in other words, your Zin is j omega L plus 1 by j omega CGS. This will give you the imaginary part, and you get a real part, which is L times omega t, where Gm by Cgs is omega t, right? So I will call this omega t times L. So this is the real part, right? So if we choose omega equal to some omega naught, at omega naught, I have 1 over root over L. So if we choose this, then Zn at omega naught is purely real and is equal to omega t times L, right? So you essentially get a match without any additional noisy element, right? So again, to quickly recap, so what did we learn today? So we saw that what is the impact of noise figure from system perspective, right? Then we saw that it directly impacts the sensitivity of our receiver, which is the minimum amount of signal that I expect at the input of the receiver to make sense of the output, and noise figure has a direct impact on that. Then we went back to our networks, low noise amplifier networks, with the example of a common source amplifier, which gives us gain, but it does not give us matching. So in order to give matching, so we put in a resistor R, and we found out the noise figure, and it appears like the noise figure cannot go down below 3 dB, right? And it will obviously be more than 3 dB because we get the 2 plus an additional term. And the reason of the 2 plus was the fact that we had a matching resistor which was also noisy. So then we were looking for a way of figuring out if we can actually put something to good use, which is not noisy but can give us matching. Then we saw a way, probably if we use these capacitors of the inductors, right, in a certain way, and wrap them across some sort of LTI network which has some phase lag, then there is a chance that the input impedance looking into one of the ports will have a real part, and lo and behold, we found a way of going about doing it. Now, obviously, you should from this you should obviously take the key takeaway from there is this is not the only contraption that you can make using this principle, right? And obviously you can put this together to get n number of matching networks. But as it turns out, this is one of the most popular way of matching an LNA, and we will derive the noise figure associated with this, and what are the key things to take care if we choose to make an LNA using this topology. We'll do it in the next class. Okay.